something like that.
Okay, that's good.
That's good.
Thank you, Yuan. 8 o'clock, right? 8 p.m.
Yeah, 8 p.m. is not late for me. Yeah, I typically go to bed around midnight. Yeah.
Okay. Same here. It's almost the same for most academics. Right.
Hi everyone. So our webinar is live streaming now. And Lizzie, please go ahead.
So should I share the screen or not?
So what Daisy will talk about the journal and give a very brief introduction first.
Okay.
And then I would introduce both of you very briefly, and then I think we will hand over the control to you for share screen later.
Okay.
Just in a couple of minutes. Thank you.
Okay.
Yep, thank you. Good morning and good evening, everyone. A big welcome to our EcoMat New Year webinar series. Today is our first session in year 2022, and today's topic is extreme mechanics of flexible and variable batteries. My name is Daisy Diao. I'm the journal publishing manager of EcoMat from Wiley, China. First off, please allow me to give a quick introduction about our journal. EcoMat is a flagship journal published by Wiley in collaboration with the Hong Kong Polytechnic University. It is a gold open access journal, and we aim to publish on a wide variety of topics from different disciplines that share a focus on cutting-edge materials for green energy and the environment. The scope of EcoMat is very broad, including energy harvesting, storage and conversion, batteries and supercapacitors, energy systems and networks, fuel cells, water and air pollution control, carbon capture, etc. The articles can be immediately opened at speed. EcoMat has already published 12 issues online so far since it's launched in 2019, and the article publication charges are still waived until this year's end. Our ambition is to make a mark in material science and its adjacent fields of a high academic impact. Here, I would also like to introduce a bit about our dedicated editorial team. Our editor-in-chief is Professor Zijian Zheng from Hong Kong Polytechnic University. We have 4 associate editors who are Songbin Yuan from Northwestern University, Sang-Min Sok from UNST South Korea, Qiang Zhang from Tsinghua University, and Huijun Zhao from Griffith University. We also have Dr. Lo as our managing editor based in Hong Kong. He takes care of the journal's editorial daily work. EcoMat has already been indexed by ICIE, ESCI, DOAJ, and CAS before. We will receive our first impact factor in this summer. Thank you, the dedicated editorial team, and thank you, our global board members, and all the authors, reviewers, and readers. Thank you, everyone, so much for your continuous care and support. Last but not least, we welcome you to follow our social media accounts. Please scan the codes here, and you will find out more news or updates or articles on WeChat, LinkedIn, Facebook, and Twitter. Also looking forward to your next submissions. Currently, we accept research articles, review articles, and research highlights. Now I'd like to hand over to our EIC Professor Zheng to start this webinar. Please do not be shy to post your questions in the chat box if you have. Thank you.
Thank you very much, Daisy. Good morning, good evening, and good day for everyone. And thank you very much to join us for this first webinar of the 2020 EcoMat webinar series. And it's my great pleasure to invite 2 excellent speakers, Professor Huishen Peng from Fudan University and Professor Yuan Yang from Columbia University, to talk about our cutting-edge research in super thin, super flexible, super wearable sort of batteries, materials and structures and devices. So I will be the chair today, and if you still don't know me, I am Zhijin Zheng. I'm the current editor-in-chief of EcoMat. Our journal, as Stacy already introduced, publish research articles and review articles in an open access mode, and is run by Wiley in collaboration with the Hong Kong Polytechnic University. And we look for the most outstanding works in the field of functional material for green energy and environment. So we cover materials, technologies, and sometimes a little bit of systems. So we welcome you to submit to us. We will receive our first SCI impact factor this year. So I think it's normally published in about June or end of June of the year. It's expected that the impact factor is going to be over 10. According to the Web of Science data. So we will, let me really briefly introduce the first speaker, Professor Wilson Peng. So I think whoever worked on flexible electronics, fiber electronics, fiber energy batteries, people know him very well. And he's now professor at Fudan University. He's currently head of the Department of Macromolecular Science. And I don't think I'm going to give a detailed introduction. And he has received so many awards and everywhere, right? And I think in mainland China, he's received almost everything award. And I think he has a really busy schedule. So I think without further ado, I will hand over the time to him. And before Professor Peng's talk, and I would like to encourage everybody to raise your questions. So if you are in different channels, you are welcome to raise your questions, put down your questions in a typing format. And then there are people to forward your question to me, and I will read them. Or I will summarize them into a common questions and raise to the audience, to the speakers. So, yeah, Professor Peng.
Yes.
It's now's your time.
Okay. So can you? Okay. So can you see it?
Yes. Yes.
Okay. Great. Okay. So first, I want to thank Professor Zhijie and for this very nice chance to share our research. I think yes, I do read the papers from EcoMat. I think this is a great journal. We're also trying to submit papers and hope to have a chance to publishing and to share with you some new results in the future. Okay, so today I will mainly discuss our recent studies on fiber electronics and more focused on smart fiber materials and devices. So as you know, electronic devices are the driving force of information technology, and they are becoming more flexible, neutralizer, and integrated. And if you look at this history from the first computer, and it weighted 30 tons, and to now the laptop and 70 kilograms, and possibly some people may be using it, or it will dominate our life in the future. This wearable computer system, and just tens of grams. So for this important process, and the structure of these devices are evolving mainly from 3 dimensions to 2 dimensions. In other words, we try to make this device thin, then it can be highly flexible and very important directions. And many people have made important contributions to this direction. And in the past almost 15 years, we're trying to further make these devices into 1 dimension, and it can more like fibers. And by designing these architectures, and we can get these fiber devices that can be even more flexible, can be elastic, and highly miniaturized and highly integrated. And very important, these fiber devices can be further woven into breathable textile. And currently, we have realized these 5 devices with many functions from generate electricity, store energy, emitting light, changing colors, computer, communicating, treat disease, and a lot of them. And I will share some of them to you today. And we also made many applications based on these 5 devices, and I will share some in the following discussions. In fact, there are a lot of applications I mentioned, and specifically, these 5 devices may be made the next generation smart textiles, and the European Union even named it the 4th industrial revolution, with a huge market of trainings of European. So possibly in just 5 to 10 years, and we are seeing a lot of smart textiles, mainly based on these smarter fiber devices. Okay, so then I will mainly discuss what we have done in the past years, and from these smart fiber materials to fiber devices, because first we should have fiber materials as electrodes, and then we can make the fiber devices. So we previously started from these aligned carbon nanotube polymer fibers. I belong to the Department of Polymer Science. So then we're trying to enhance the property of polymers, and especially polymer fibers. Then we try to incorporate the other functional components such as carbon nanotube. And indeed, previously, many people have done this direction. And many people just dispose carbon nanotube and polymer in a solvent, and then during a solution process, by evaporating the solvent, we can produce this important bulk materials or composite film. And a lot of people have done this kind of research, and the main problem is that the carbon nanotubes will aggregate to form network structures. And by this way, and also we try to take advantage of the high mechanical and electronic properties of carbon nanotubes. But in fact, for the component materials, they show very low strength and very low conductivity. That's a big problem. So then poor properties come from this networked structure, this aggregation. So then we try to align this carbon nanotube in the component materials and more focus on these fiber materials. We first synthesize a carbon nanotube array, and then we can spin out this carbon nanotubes to form these fibers. And during this process, very important, carbon nanotubes are aligned along these directions, along the fibers. So of course, this fiber can be further made into these polymer structures, then it can be stretchable. So if you look at the SEM imaging, and the carbon nanotubes are indeed highly aligned with each other, and this is just the first level fiber can be further made into this polymer fibers, big fibers, and then we try to also incorporate these functional polymers, and we are more focused on these chromatic polymers. Here I just give you an example. This is Dyson molecules, and they can be collected to the carbon nanotubes, and very simple reactions, and then on the UV light, and they can go on top of chemical polymerization to produce polydiesterone, and for the result. Composite fibers, and very interesting, the ice prepared composite fiber is blue. And when we pass with the electric current, it quickly changes the color to red. And the color change is totally reversible and very quickly, in just less than 1 second. And this is the first example. We try to induce the color change based on the electric current, and the mechanism, and we try to understand, although it's still not very clear yet. And here's carbon nanotube, here's our polar Dyson molecules. And as you know, when you pass with the electric current, carbon nanotube is conductive. So that they will form this electric field. And the electric field will induce the side chain. We design these polar groups, and the side chain with the equalizer to induce the conformation change of the backbone. And therefore, the electrons on the backbone, when they try to resolve the transition to pi star, and they will absorb different wavelengths of light, and therefore microscopically we will observe the color change. Anyway, for this copper fiber, very interestingly, and we can use just 5 volts to induce the color change. So they can be made into these clothes, and clothes can change colors to show different patterns. So you can have different styles of clothes. So in the future, possibly the fashion shops may disappear, because just based on one clothes, you can get what you want. And this is very interesting direction, and we are commercializing these materials. And this, the next is about this deformable composite fiber. They can change shape. And we just designed the monomer as benzene, and you know they can go on trans to cis transition. And during this process, the length of this unit will change by about 2.5 angstrom. So if these monomers are polymerized and oriented together, and microscopically we will observe the shape change. It's just the scheme to show the figure to show the new emissions to induce the shape change by UV light. So a lot of researchers, but our focus on is we try to control the direction of the shape change by simply tuning the space of the aligned carbon nanotubes. So if for the composite materials, if the distance between 2 carbon nanotubes is higher than 20 nanometers to 15 nanometer, and the mixture based on benzene is aligned along the length direction of the carbon nanotubes. So on the UV light, they will bend into the light source, and so the shape change will like this way. However, if the distance is reduced to 20 nanometer or no, and then the mixture will be aligned by the potential to the length direction, and by this way on the UV light, and the composite materials will bend away from the light source. So it's very simple to control the bend direction by just varying the space between carbon nanotubes. And also interesting because this material is also conductive. So then for this fiber materials, when we pass with the electric current, very interestingly, the fiber will show 2 very interesting actuations. First, they will rotate, and the carbon nanotubes are aligned with by this way, and here is the helix direction. So during this process, the helix angle will become higher, and the fiber will become more tighter, and also there is a shearing along the length direction. So there are two actuations, and it's highly reversible. And we also try to understand what's going on. And very similarly, here are the two carbon nanotubes, and when part with electric current, and there will be electromagnetic interactions in this direction. So then it can be divided 2 forces along the length directions and also another as this direction. So then we have 2 actuations. And very interesting for this fiber materials, we think they are very promising artificial fiber muscles because they can generate strength more than 260 times of the natural skeletal muscles. So we are trying to use them for these soft robots. You know, the robot previously are very rigid, so now the robots are more like people and more like new human beings. And for these soft robots, we need this very important, very lightweight, and very strong fiber muscles. Okay, so then for this fiber materials, I share you with very high mechanical and electronic properties, so they can be used for fiber electrodes. Then we try to fabricate a lot of fiber devices. The first direction I show you is fiber energy harvest and the storage device. For this energy harvest device, and we mainly design two kinds of structures. One we call coaxial structures, and we more focus on the solar cell and show you as the typical examples. Here's one fiber electrode. Then we coat this photoactive layer on the surface, and here is the second electrode. Here we use a metal on the surface, and if you use unzip along the left direction, and it should put a similar structure to the planar solar cell. And for this same second electrode, it's not easy, especially when we want to get this continuous, very long fiber device. It's very challenging because the film may break because it's very thin. If you want to make this thicker, it will not be transparent. So there is a balance. So then we try to replace this very thin, unstable electrode with another fiber electrode by this twistor structure. Then it will be much easier for the continuous production. Okay, I will show you several examples about these solar cells. Here, first I will show you this Dyson solar cell in the fiber shape. And here is the structure, one fiber electrode, and here is a lot of fiber electrode, and we use this dimolecules and the active layer on the surface of one fiber electrode. And here then we twist them together, we can have this fiber device. And for the fiber solar cells, it's very important that one fiber electrode should be very flexible. Otherwise, if the two rigid fibers are twisted together, you know, the interface will be very poor. And then it will be very difficult for the charge transport at the interface. So here we choose the carbon nanotube fiber. It's very flexible as the one fiber electrode. And here a lot of fiber electrode can be carbon nanotubes or the other fiber materials with the active layer on the surface. So it can be you can see the interface is very good. And get this fiber Dyson solar cell, can weave them together or weave with the other chemical fibers. And for these fiber solar cells, there are some very unique properties. Here I give you several examples. For example, here I show you for the active materials, if they are on the fiber electrode, if they are sphere, you will see that on the elucidation and the photoelectron will transport through a long pathway. And for this for this nanotube or nanorod, and it can be very short path length. And more important, this nanotube or nanorod will go in your this radial direction. And as it's here is the space increase, so the active dimolecules can go through and go to this bottom. So for this whole electrode, it can be very efficient. And if it's planar, and it's very difficult for the dimolecule to go to the inside. So for the planar solar cells, people will tell you for this kind of structure, it shows the highest efficiency. And for our fiber solar cell and for the nanotube or nanorod, we find the highest power conversion efficiency. And also for the fiber solar cell, it's very long, and especially for the new applications. And for the planar solar cell, it's a very short distance for the charger to transport. So we try to understand how the charger can very quickly and efficiently transport along the long fiber electrode. And it is, and we show it's a 3-dimensional hopping model. I will not go into the details. And for the Dyson solar cells, we mainly use the liquid electrolyte for high power visual efficiency. It's not good. So then we more focus on this polymer solar cell because it's totally solid and it's easy to fabricate. And the main change, we use this Kindard polymer as the active materials. And the structure is pretty similar to a Dyson solar cell. And here is a fat polymer solar cell without sealing, and you can see it can be highly flexible. And after bending for 1,000 times, and the power visual efficiency can be maintained by 90%. And of course, for the polymer solar cell, the problem is that the power visual efficiency is negatively low, although it's solid. So then we come back to this perovskite solar cell. Many people are doing this kind of studies, and we try to make them into fiber, and we expect it can show high power visual efficiency, and it can be also solid. And indeed, we can get a very high power visual efficiency. But the problem is that about this stability, safety, and a lot of things. So for each types of solar cells, they have their own advantage and disadvantage, depend on the applications. So far, the highest power visual efficiency is about 12%, and it's good enough for applications. So although it's lower than the planar solar cell, but for the application, it's okay. So we are now trying to scale up, mainly how to maintain the power visual efficiency when it is scaled up. And for the fiber solar cell, there is also another very interesting advantage. And the power visual efficiency is independent on the angle of the incident light, because it's one direction, and when the light emitted from different directions, you can expect that the emitted area is very stable. So then we will say that the incident angle change from 0 to 118 degrees, and the power conversion can be well maintained. Okay, so based on these fiber solar cells, if we use them to weave textiles with coverage over 80%, and it can produce the electricity to power 36 cell phones, and it's good enough for many applications in the real life. And also, the fashion area think it's a very interesting direction, and they think it will be a huge market. So previously, this companies they organized a fashion show based on these wearable solar cells, and the CEO sent me these photos. And if you look at the solar cells, they are mainly silicon solar cells, and they are not nearly weldable, and just a conception. So he said, based on the fiber solar cells, it's nearly what they want. So we're trying to go along this direction. Okay, then we have the electricity. We should store it. So all you know, we should make these fiber batteries. Of course, it's not easy, because from 2 dimension to 1 dimension, the electric field, charge transport, and interface are totally different. And if you look at the private batteries, and here is 2 electrodes, and the electric field can be very uniform, and it's very easy to design active material to match them. However, for these fiber batteries, if we learn from the fiber solar cells, we design the twistor structure, you will see that the electric field between 2 fiber electrodes, okay, so I'm sorry, will be different. And also similar to solar cell, the charge transport is very long life duration, and especially during the fabrication and also during the use, the interface between two fiber electrodes, how to make them stable. It's not easy. Okay, so here I will just show you how we solve the first problem. And here is the electric field for this polar solar cell batteries. And here is the case for the electric field based on two fiber electrodes. It's not uniform and it's not easy to match the active materials. So based on the simulations and the experiments, we show that if these fiber electrodes can design this hierarchical aligned channels, and then it's possible for them to form this uniform electric field. So then we try to design this fiber battery model by design this unique fiber electrodes. Here is just one example. I will say we use this called hierarchical and helical assembly to make this composite fiber electrode. Here's the one case, for example, carbon nanotube can be twisted with this active material to form this one level fiber materials, and then it can be the first level fiber can be twisted into larger fibers, and even this even much larger spring-like fibers. So you will see that there are a lot of channels, aligned channels, and here tens of nanometers between carbon nanotubes, tens to hundreds of nanometers between two second level, between first level fibers, and even these very larger channels. So then we can have the required junctions to form this uniform electric field. And also, you can see that based on this multi-leveled channels, the electrolyte can be very efficiently transported first through this larger volts, and then small volts, and the tiny volts. So it's very easily and very quickly, and also with very high efficiency for the electrolyte to go into the fiber electrode. So the charges, the ions, can be transported very quickly and efficiently. And then we also want to try to solve another problem. We should use gel electrolyte, because for liquid electrolyte during the fabrication it's not easy, and also the safety problem is very important, because for many fiber batteries we mainly use them for wearable applications. We touch with our skins, with our body. So we are trying to replace this liquid electrolytes with gel electrolytes. Then we find a very effective solution to this problem, and we design monomers first, and the monomers are liquid and can infiltrate into the fiber electrode and also into the batteries. And then after in-situ polymerization, they form polymer gel electrolyte, and then we will have this semi-solid fiber battery. So then we try to get this first fiber batteries in 2013, and it can be continuous, but the property is very poor. So then we try to optimize the interface, the materials, and especially use fiber electrode with much high conductivities. And then we can get much high performance fiber batteries. And we can even make them by continuous facility. We can scale up now. And here two fiber electrolyte and electrode, and through this electrolyte, and then for one fiber electrode, we just use this wrapping them separate and twist them together. Here's a new production line, and we can produce these fiber batteries for about 50 tons every year. And you can see that the fiber electrode can be very uniform. And of course, we have solved many problems based on the surface and interface. For example, the active material may be not uniform on the fiber surface, so how to make them uniform and how to make them very stable on the bending. And we can produce at a larger scale here a lot of fiber batteries. Here is just one fiber battery to show how it looks like in the new case. And the more important, when the fiber batteries is increased, and you can say that the spatial capacity, the capacity can be linear increased, and also it can be show what we designed and very nano distribution, and we can very easily control and design the electrochemical properties of the fiber batteries, and also highly flexible after bending for 100,000 cycles, and the capacity retention is still over 90%. And more important, the energy density can reach 124 watt-hour per kilogram, and it's based on the totally fiber battery, and so it's almost based on the products. Although it looks lower than the bulk batteries, we're trying to still increase them, and also for this value, it's good enough for many applications. And for the previous method, although we can produce a long fiber battery, the production rate is relatively low. So then we try to learn from this chemical fiber, the production process, and then we can very quickly produce the fiber battery with very high speed. These the fiber batteries are woven into textiles, and I will not go to the details. And for the battery closes, and it can be used to charge over 52 cell phones. It's good enough for many applications. And here show you the videos when you soak it in the water and then twist it, and it's stable and effectively work. And here also, okay. So on the punching, and it's still very stable. You can see that no problem, and can stably work. And also we can even integrate with some wireless charging unit, and then for this battery textile, just put yourself on it without the correction by wires, and can be a very efficient charge. Okay, so then I will go to very quickly. I don't have enough time, and so for this light emitter fiber and test display, and very similar to the solar cell. You know, solar cell from solar energy to electricity, and for the this lighting device, and from the electricity to emit little light. And here I show you a Co-Extrusion, not the twisted structure, and the fiber electrode and active layer on the surface, and here another transparent second layer. And we can say, and for the first example, it's not flexible enough, and then we try to use this extruding process based on solution. We can get this flexible and very highly stretchable lighter fibers, and you can see that, and very high stability, high strain, it can still work stably. And we try to use them for many applications. For example, based on the one-dimensional structures, we can use it to precisely stimulate the levels, and it's very efficient. And also, these lighting fibers can be woven into textiles, and then for the treatment of these jaundice, it's a very interesting application. And then we also try to get this display textile. It's still not available previously, and we designed these kind of structures. Two fiber electrodes are woven together, and the active materials on the surface of one fiber electrode, and then we part with the electric current, and the contact point will emit light. So it's more like a pixel. So we have a lot of pixels on the textiles, and then we can get this very flexible displays, highly flexible, and it's very easy for the new productions. And I will not go to the details, and we even can wash them based on this high requirement standard and no problem. And we also try to understand the mechanism beside for this display textiles. Okay, so here's the applications. For example, can use on the sliver to as a electron map, and can be used to communicate. We can make it safer into the textile, and also can use it for the communication. If you cannot speak and you wear this text display, and the brainwave can be transmitted to the signals and to show on the clothes, so that other people can very easily, efficiently read it and communicate with you. And also fiber sensor, and based upon a similar structure, but use just active material are different, and can be then design this sensor in response to different ions, glucose, and pH, and then can be integrated together into these clothes and show the signals when you are expressing. And it's very highly flexible and very stable and also very safe. So we can even inject this fiber sensor into the body, and also very highly stable and some very unique properties. Okay, so then I still have 3 minutes. I show you how we integrate them. So for the first case, we can mimic the initial year, and we just, for example, connect many of supercapacitor unit or battery unit together just in one fiber. And then based on the unit with the increase, and for this just one fiber, it can output very high voltage, 200 volts or even high. And we also just based on the same fiber substrate. Here is the photoactive materials. Here is the electrochemical active materials. Then we have the harvest energy, storage energy, and or even can incorporate sensor on the fiber. And also very interesting, we can twist 3 fiber electrodes, and with 2 together, and it can be a high, can output high high power and high power density, and here high energy density. So we then have this 2 high power density and high energy density together, just in one device. And also I mentioned we can weave different types of fiber devices together, and we can have this smart textiles. Okay, so I was summary. We started from 2008, and we have made over 20 different types of fiber device, and we try to start the unique interface based on different interesting architectures from this fiber electronics. And a lot of people are trying to solve to make researches around the directions, and of course there's still several remaining challenges. I just very quickly go through them, and we should design some material specific for the fiber devices, how to further enhance the properties of fiber device, and also how to design some characterization facilities specific for fiber device, how makes them at a larger scale, and further integrate them together at a larger scale. Okay, so I think it's put the time, and I want to thank a lot of cooperators and also funding support. Especially, I want to thank our lab mates at my lab, and thank them for the hard work. Okay, so I will end the speech. Thank you very much.
Thank you very much, Professor Peng, and that was a wonderful talk. Cover almost everything, right? Fiber-based electronics devices, energy harvesting, storage, sensors, display. So I think there are many questions. So I will ask maybe 2 very detailed technical questions, and then we'll put the rest after Professor Yang Yuan's talk.
Okay.
So there's a specific question asked about the strengths of your CNT network yarn.
Mm-hmm. Yeah.
So I think the question, I'll rephrase a little bit, is one is that most of your reports show that the strength is less than 100 megapascal. How strong is it? And in terms of the strength, the modulus. Another one is the 2-axis. Is it a big difference for this kind of fiber?
Okay, so for the strengths, and currently for the mechanical strengths, and it's over 1 gigapascal, and much stronger than most chemical fibers. So it's strong enough. It's no problem. And of course, some research labs can even get this carbon fibers with strength of tens of gigapascal. Of course, it's not easy. I mean, not easy for scale up. And for the continuous larger scale carbon fibers, it's no problem for over 1 gigapascal. And it's strong enough for the applications I mentioned in my speech.
Okay.
Yeah. Okay.
I think that's one question. And another one is how to ensure the uniformity when you make this composite fibers and yarns in terms of, some of your results show that you can get a good penetration of different materials, and some of them you show that you can wrap the materials with some functional sheaths, right? And how do you ensure all this uniform, encapsulation or wrapping or compositing?
So far I will show how we make them. With this connective array, and we pull them out, and during this process, and it's just a sheet, and you can coat polymers or monomers on the sheet, and then twisting to form the composite fibers, and so we can get this very uniform composite fibers. It's also for the uniform film. And if we just want to design the materials just on the surface, so first we just pull out the carbonated fibers and twist them very tightly, and then we can coat the active material mainly on the surface. It's not easy for the active material, especially for the polymers, to go inside. It's not easy. So then we can design this co-shear structure. So I think it's easy to design different structures, no problem.
Right. I think there are some other questions, but I think I will put it at the end, because this question I think is more related to the design, the overall design, overall advantage or disadvantage of fiber electronics or batteries or cells. So thank you again, Professor Peng. Please wait a little bit, and then we'll hand over to Yuan. Yuan, are you ready?
Yes, I'm ready.
Yeah. Yes, thank you very much. So let me introduce the second speaker, Professor Yuan from Columbia University. He's now in the Department of Applied Physics and Applied Mathematics. So Professor Yuan get his bachelor from Peking University and a PhD from Stanford, and then a postdoc from MIT. And now he was an assistant professor, right? Starting in 2015, and very, very quickly he was promoted to tenured associate professor in 2020. So this is considered as a fast track to exceptionally outstanding researchers in the top 10 university in the world. Now, Yuan has been known to his contribution to this mechanical design or structural design, and then a basic fundamental understanding of materials and devices for electrochemical energy storage devices and conversion devices. Some of them are for thermal management as well. So I think today he will focus a little bit more on this batteries. So Yuan, please, I think I'll hand over everything to you.
Yeah, okay. Thanks for the introduction. Let me share the screen. Okay, I assume everyone can see my first page. Can hear me? Okay, great. So first I will thank EcoMat and Zijian for the invitation. I really appreciate it. And also Professor Peng just gave a very, very impressive talk on flexible electronics. And my talk will focus more on the battery part, and my design is more bio-inspired. And today I will not only cover flexible batteries for wearable electronics, but also think another extreme in terms of mechanics. So that's the structural battery, which means we want to make batteries actually really mechanically strong. So this is can be used to replace the structural components in vehicles, airplanes, and can also be used for wearable devices, for example, in a helmet. So before I talk about these two types of batteries with extreme mechanics, I want to give an overview of research in my group. So I sort of have a diversified portfolio. The major focus is on batteries, and it spans from in situ categorizations. We try to understand the actual chemical process inside at different scales. For example, we develop some very advanced Raman microscope so that we can see how the lithium metal dendrite formation is related to the ion depletion in the electrolyte. And also solid-state batteries, we design materials to stabilize the interface and improve the performance of solid-state batteries. So the flexible structural batteries is batteries with extreme mechanics, and that is the topic I'm going to talk about. Besides batteries, as Zijian mentioned, I also work on thermal management. That's from my postdoc training. And basically, we try to make some radiative cooling paints so that it can fully reflect sunlight and also emit heat to the cold sky. So that means without any electricity, the surface actually can be cooler than the air, even under very strong sunlight. Okay. And today I'm going to share two bio-inspired structures with you. The first one is spine-like flexible batteries, and second one is tree root-like design for the structural batteries. So let's look at the flexible batteries first. As Professor Peng mentioned, the flexible electronics is actually a very exciting new field, and the market is growing rapidly. For example, we want our cell phones to be flexible, and also we want our clothes to be part of the sensing system, and those sensing wearable devices can be integrated with the clothes seamlessly. So that also requires the electronic devices to be very flexible, and for example, in the display. So, and to make these things flexible, actually the batteries, flexible battery is a very important part. Currently, we have this such as the foldable phones on the market, and where the batteries actually don't have to be flexible because you can put it on part of the one half of the device. But in the future, so if the electronic device become fully flexible, actually it's desired to have the batteries to be flexible at the same time. And moreover, for these wearable devices, if we want the whole device to be seamlessly integrated with our body, then actually batteries need to be flexible, otherwise the device will not feel comfortable. But why is battery not flexible? Okay, so this need to go back to the basic structure of batteries. Professor Peng mentioned this a little bit. Basically, in batteries, we have two electrodes. They are made of powders and sit onto metal foils. And they're also separated by a separator to avoid the shorting between the two electrodes. So when these electrodes and separator sheets are made into a cell, they are either wind together to form a sort of prismatic cell, or they actually stack together to form a stacking cell. So if we look at this individual component, they're actually highly flexible. You can see from here, this is the lithium cobalt oxide positive electrode on aluminum foil, and the separator is just a very thin polymer. So why is battery rigid instead of flexible? The reason is actually the thickness. So we want to make battery thick so it can store more energy inside. But when you bend the battery, the string inside is actually proportional to the thickness over twice of the radius of the diameter. So then for a battery with size about 2 millimeter, so that's similar to thickness of battery in cell phones. Even if we just bend it down to a diameter of 5 centimeters, the strain inside is up to 2%. And this is also confirmed by simulation. So you can see that the strain can reach about 2%. And such strain is much higher than the tensile strain in metal foils, such as aluminum and copper. So tensile strain means the reversible range of strain, so that the materials are not damaged. And the bending actually will also cause the sliding between different layers. And such sliding induced shear strains are also not good for the actual materials. And more importantly, so the tensile strain and stress of materials actually will also decrease upon many cycles of bending. So from this plot, you can see that when the cycles reach about 10,000 or 100,000, so that's actually desired for flexible devices. So the fatigue stress actually will be only about half of that at just one time of bending. To solve these problems, there are several kind of strategies. For example, we can reduce the thickness, so it's very straightforward. You have thin cells, and then the strain inside will be lower. But because battery always have a package, so that if you just have, for example, one layer of the actual inside, the energy density actually will be reduced a lot. So, and also, for example, people use carbon-based materials as a flexible substrate. That can solve the problem partially. Carbon materials often have a low conductivity and also can take actual weight. So Professor Pong showed this very innovative and exciting designs, wire-like batteries, so which show very good performance. So these strategies often are with significant redundant volume, so that the energy density is reduced. Now, of course, Professor Pong actually showed a recent very exciting progress that the energy density is actually improved a lot. So I think the values are very promising for practical applications. So we think that for flexible batteries, we actually need to pay attention to three important aspects. So first, the flexibility. Okay, so that means the cell needs to reach a bending diameter of from 1 millimeter to 10 centimeter, depending on the application. And the bending times should be reached by 1,000 to 100,000 times. So it also depends on the application. So energy density wise, it's ideal to have an energy density over 80% of conventional designs. So because the number one requirement of battery is actually the amount of energy stored inside. And regarding to power, it also need to have a stable output power during the dynamic flexing, so that the power is very stable. It's not affected by the mechanical deformation. So to try to reach to satisfy all three aspects, so we actually inspired by the structure of spine. So try to decouple the energy storage and the flexibility. So basically, in spine, spine has two parts. The solid rigid part is called vertebrae. Okay, so it's actually a hard component. And the reason why spine is very flexible is that they are actually called the intervertebral discs. So that's the soft part to connect those hard parts together, but to make this hard vertebrae to be flexible. Then basically in our design, we have a thick battery part, so which is actually not flexible, but since it's quite thick, so the energy density is high. And also we have this linker, so which is a soft components, so that can make the whole battery to be flexible. You may ask, why don't we just link many small batteries together? The reason is that for in battery, so when the battery is small, so the packaging actually will be a significant part. And if you have a big battery, just many very small parts. So the packaging mass actually can be reduced to enhance the energy density. And to make such spine-like structures, we actually first cut the electrode and separator to the brush-like structure. And then we wrap the teeth onto the backbones, so that we finally form a spine-like structure. So then actually the system can reach about, in theory, can reach about 80 to 90% of energy density of the conventional cells and can make it to high flexible. And it's also a single cell, so no need to integrate many small cells together. So that also makes the whole process simpler. So with such design to validate that it actually can be flexible and the strain inside is low, we run finite element-based analysis based simulations. In the prismatic and stacking cells, you can see the strain inside is pretty high, it's 2% and 1% respectively. But once you make it to the spine-like structure and due to the flexible interconnect, so actually you can see the strain inside is very low, so only about 0.08% left. And the twisting and during the twisting, so the strain inside is also very low. Okay, then this strain left is much less than the tensile strain of the metal substrate. So that means it actually can be pretty robust, and we don't need to introduce new materials inside. So the cell, we first test them in the static condition. Okay, and you can see the cycling is pretty good. The capacity return is about 6% after 100 cycles. And during the cycling, we also try to bend it for many times. So 10,000 times here, and do the twisting for 1,000 times. And then we test the performance in a static condition, in the flexed condition, and in the twisted condition. So you can see the power output, the cycle life, the capacity is quite stable. So, and the voltage profile is also very stable. So you can see that there's almost no change. So when the battery is placed into different chips. We also open the cell after after 100 cycles and look at the corner of the interconnect part. So here is where the strain is highest in the cell. Okay, and if you look at the SEM, you will see that there's no crack or no damage to the particles, even at a microscope, microscopic scale. So that means indeed the strain inside is very low and doesn't affect the performance of the doesn't affect the electrochemical performance. As I mentioned, so not only needs stable power output in the static condition, but we also need stable power output in the dynamic condition. So we also run this cell, charge and discharge it when the cell is under dynamic banding for many cycles. And you can see that the voltage is very steady, so the change is less than 10 millivolt. And on the other side, if you make a prismatic cell with a similar size, actually during the banding, so this is banding down to, I think, radius of 3 centimeters, so the same as the left one. So the voltage actually will fluctuate a lot. So this is actually not acceptable for variable devices. And the battery also have a pretty reasonable power output. The rate performance at 3C. Okay, the discharge capacity is more than 80% of that at low rate. So we further run this dynamic test, cycling test. So this cell, you can see that it's actually so in different stage. Okay, so here is band, and here is the flat state. You can see that the capacity is quite steady. So during these 10 cycles, we actually bent the cell by 3,000 times, and the voltage profile is also quite stable. So compare with the literature, so I think this structure, the advantage is first, it not only have a growth cycling life, but also the energy density is attractive. So 240 is not a very high value actually. That's because in our lab demonstration, the mass loading of the active material is about say 1 million hour per centimeter square. So if we push it further to 3 million hour per centimeter square as the standard commercial lithium-ion batteries, I think this number can be improved. And currently, we are also trying to commercialize it. We collaborate with a company and try to make the standard cells that you can see from this is a cell prepared by the company. Okay, and so in this cell configuration, if you take even all the volume between the different segments into account, so the energy density is between 250 to 350 watt-hour per liter, and if you just consider the volume of the segments, so the energy density can reach about 550 watt-hour per liter. So that's similar to the standard lithium-ion batteries. And also we can reach binding radius of 10 to 30 millimeters and binding times over 50,000 times. And this is a test. So you can, from the number here, you can see that it's 8,000 times. And the dimension and capacity can be changed based upon the demand. So and the company is also hiring battery scientists. If you are interested, feel free to contact the company. So it's based in Shenzhen. And we can also modify the spine-like structure to make it according like. Okay, so basically in the interconnection part, so we can make them into a zigzag, so they can actually be stretched. So we also show that during the stretching, so this 5,000 times of stretching upon 10 cycles, the capacity is actually pretty stable. And such segmented structure actually have another advantage to reduce the heat generation during the thermal runaway. And the reason is now the cells are actually separated into different segments. So even one part encounters the thermal runaway, or say loss of heat generation, it actually will have less effects on other parts. So here is a demonstration of charged battery. If you use a nail to penetrate it, okay, so actually you will not see any thermal runaway. Okay. So the design can be further modified to this foldable batteries. Okay, so that you have a folding, and this can reach a high energy density and also can be folded down up to 180 degrees. So and also the power output is very stable during the folding. This is another demonstration to show that we are making a cell with capacity similar to commercial cells. I think the capacity is something like 300 or 500 milliamp hour inside. Okay. Okay. In the second part, I'm going to talk about the extreme mechanics on the other side. So how to make battery really rigid. Okay. So and the application of the structural battery is that we try to use it as a structural component in vehicles, in airplanes. And recently, BYD showed this blade batteries, and this is also can be considered as a part of the structures. And the structural battery will focus more on materials inside the battery instead of outside the batteries. And for structural battery, if we make battery really rigid, then it actually can also be used for wearable devices where we actually need such rigidity. For example, helmets to protect our head. So if the battery can be really rigid, then that can makes the helmet smarter, so that to integrate more functionalities inside. So and to make the structural batteries, okay, to replace the structural components. Then that means the batteries need to have really good mechanical properties, for example, tensile properties and the rigidity upon impact. And at the same time, the actual chemical performance cannot be significantly compromised. So and in our study, we particularly focus on the bending modulus and the stress. So, and the reason is that bending is actually a particularly weak properties of batteries. So what's bending modulus? So this actually describes the capability of a battery or some materials so against a bending force, and it's proportional to the ratio of the bending force over the deflection. And we can see that it's also related to the dimension of the cell. So for example, it's proportional to the cube of the length and inversely proportional to the cube of the height. And the reason that batteries has pretty bad bending performance is that batteries are made of these multiple layers. So when you bend it, this is actually like bending a thick book. Okay, so because the different layers are not laminated together, so it's actually very easy to bend it. And if you do some quantitative measurement, so the bending modulus is actually even less than the common polymers, such as polyethylene. Okay. And this actually originates from the relative sliding between different layers in a battery. So we do need to find the mechanical properties of batteries and also reduce the relative sliding between different layers inside. So there have been some previous strategies. So for example, we can put carbon fabric inside. Carbon fabric is made of carbon fiber, so it's actually very strong materials. But the problem is that the carbon fiber typically not have a good mechanical doesn't have a good electrochemical performance compared to, for example, graphite, and also it can increase the weight significantly. So another strategy is to have some rivets inside. So the rivets will connect the top and bottom of the packaging. Okay, so that basically to fix the top and bottom the packages, so that when you bend it, so there will be almost no sliding between different layers, so that the mechanical stress can be enhanced. But this process is actually not easy to fabricate, so it has a very complicated fabrication process. So we are just inspired by how tree can be stable against the wind and use a tree root-like interfacial adhesion. So try to make the batteries more rigid. So basically, with the interfacial adhesion, you can see that this is a anode separator cathode tri-layer structure. So that can withstand its own weight. But if you have no adhesion, so the battery actually cannot withstand its own weight. And basically, the wind, so against the tree, is like the shear stress during the bending process. And the white tree is very stable against the wind. That's because the root is deeply into the soil. And soil is like the actual particles. And they need to find something like the tree root structure so that can penetrate into the powders, into the particles, and also laminate the separator together. To demonstrate this process is valid, so we first run some simulation to show the improvement in the bending force against the deflection of the cell. So basically, the slope of this line is proportional to the flexural modulus. So without any adhesion, just in conventional cell, the bending force is very low. So that means the modulus of the battery is low. And if we use carbon fabric, so which is a common method to enhance the property of structural battery. So even if we use them as two electrodes, so the binding force is only increased by 4 times, so it's still not very strong. But if we just have interfacial adhesion between different layers, so you can see that the binding force is actually can be enhanced by 10 times, so 1 order of magnitude. So that's actually a pretty high improvement. And the reason is that now all layers are laminated together, so it's like we laminate all pages in a book together, so that the book actually will become like a brick, so make it pretty strong. And to do it, we dissolve PVDF HIP. This is a polymer, so the battery field should be pretty familiar with. So onto the actual surface, and then by tuning the viscosity and also the porosity of this film, we can let it go to the actual deeply, and then use hot roll press to integrate the separate together with the actual particles, and finally. So laminate all layers together. And if we look at the penetration of these polymers into the electrode, so we can see the fluorine signals inside. So because we use alginate as a binder, so there's actually no, and use graphite as the electrode, we actually have no fluorine from other components. So the existence of fluorine inside the electrode indicates we really have the polymers penetrating into the bottom of the electrode layers. And this layer is also porous. That means the electrolyte can also go deeply inside. Okay, so basically we use this simple solution process to form the tree root-like interfacial adhesion to make the batteries stronger against binding. And from the binding test, we can see with the adhesion, so the binding force is actually about 10 times of a conventional battery, and the modulus is about 3 gigapascal. So that's actually similar to epoxy, and epoxy is a well-known structural polymer. So that it means it has a property approaching the structural components. The battery, so since the introduction of this polymer is compatible with the electrochemical environment in cells, so actually you can see the cycling performance is very good. Okay, we get 96% capacity retention after 500 cycles with standard graphite and NMC electrodes, and the voltage profile is also pretty standard. The power density is also not significantly compromised. The energy density wise is only about 5% less than commercial cells, so that's a pretty high value. And finally, to demonstrate, one step towards practical application, we make this airplane with these batteries as a wings. So if you just use conventional battery, so the wing actually is not mechanically strong enough so that it actually cannot give you a steady flight on the sky. Okay, and these cells use standard materials with a high mass loading, and one wing is actually have nearly 1 hour capacity inside. Just show you a simple demonstration. So this is the conventional cell, so it's actually cannot fly in the sky. And this is with the electrical wing, the structural battery. So you can do a reasonable job. Yeah. Okay. To summarize my talk, so in the first part, I discussed the flexible battery, and it's basically important to have flexibility, power, a stable power output, and a high energy density together. And we demonstrated this spine-like structure, so which has the potential to achieve the 3 points simultaneously. And also on the other side, so it's also attractive to make battery very rigid and can have lots of application, not wearable devices, but not only wearable devices, but also vehicles and airplanes. And with a simple engineered, so strong adhesion at the interface between different layers in a battery, we actually can enhance the flexible modulus of a battery by over 10 times and have a steady battery performance. And I think this is one of the highest reported specific energy in structural batteries. And the process is also easy to scale up. Finally, I would like to acknowledge my team and for the flexible battery part. Specifically, I would like to thank Guo Yuqian, who is a previous visiting student, and now I think he's an assistant professor in Zhongshan University. And Changming was a master student in lab in the structural battery. So Tianwei is a PhD student in lab who actually contributes most to the structural battery part, and also my collaborators. Professor Xi Chen, who is an expert on CAPS, who help us a lot on the mechanical simulations and also the funding sources. And thank you very much for your attention. I look forward to your questions.
Thank you very much, Yuan. Excellent talk about the structure design of making high energy density and very flexible battery. And I think this is typically a trade-off in this flexible battery field. Now, I think the questions are coming up slowly, and one question is about this material mismatch during the bending. So I will start with all these kind of detailed questions, and I hope that Professor Peng is still around, and then we will expand the question a little bit to the broader scope, and we will come for discussion. Now, I think for typical for Yuan's talk, and the specific questions about during the banded cell, is there any mismatch issue between the materials? And you come up with many layers of laminates, right, structures, and how do you tackle that problem?
Maybe Professor Peng can go first.
No, I think this is a question to you.
This is
yeah.
Okay.
So the specific question to your work about when you're doing this bending, is there any issue about material mismatch or in the thickness direction, I think?
I guess this question is for the structural battery part. Actually, so if there's no adhesion between different layers, yes, indeed, there will be sliding between different layers, and that actually will make the active materials easier to peel off from the metal substrate. So that's actually a problem. And if you have a strong interfacial adhesion, so it's basically like to laminate all pages in a book together, so the sliding is actually will become less. And another important thing is actually the packaging. Okay, so because they are made of the pouch, so during many times of bending, so there will also be strain in the packaging, and that's actually another problem. And that's actually another not easy to tackle problem with Nordics. Right. The packaging part is actually not easy. It's actually need to pay. More attention should be paid in that part.
Right. So I think yes, Professor Peng is here now. I think so. I would like to use about maybe 20 minutes, and then we discuss a couple of questions. Now, I personally also work on flexible stretchable batteries, as you know. So I think in this field, one major issue is the trade-off. It's always been the trade-off about energy density, either by volume or by mass, versus flexibility. Now, flexibility meaning maybe multiple dimension flexibility. For example, Professor Peng's fiber-shaped battery has addressed this problem very well, and Yang Yuan's battery looks like the energy density is much higher, right? But then the problem is for two-dimensional kind of substrate, it will be very difficult to bend or to be, we'll say, complying to a three-dimensional shape. It's more difficult to do so. How do you think about all this trade-off? Is there any perfect solution that we can fix the energy density, the omni-dimensional, pliability, I would say, right, for a wearable format? And then in this kind of idea, how do we move forward?
Okay, so maybe I just first discuss some ideas. I will focus on the fiber batteries. So maybe Professor Yang will focus on thin film battery. For the fiber batteries, the flexibility is an important issue, but maybe it's okay because generally for fiber batteries, it is flexible. And if you want to be very flexible, especially more like even comfortable than even clothes. So for this case, we are more focused on several parts. So first, if we make these fiber batteries to be as thin as possible, for example, just 10 microns, and then it is very highly flexible. And if it's big, and the flexibility will decrease. So the size is a key issue for the flexibility. So depend on the application. If you, for example, 7 steps. So first we try to use this very safe fiber batteries in vivo. We cooperate with some hotter doctors, and for this case, they want to be very thin, very highly flexible fiber battery. And then if we move the application to on the skin, just on our such as clothes, not limited to clothes, put them to the electric skin, just very close touch the skin, and the size can be tens of microns, and it's fine. And then if we just use for wearable applications, for example, we try to make the batteries into a packaging or some other bagels. And for this case, and the flexibility, and it can be hundreds of microns or millimeters, no problem. And it's just can bend, but not very. You need a little strong strength, but it's okay. So here's one case based on the size, and I think this is the main point for the industry. We do cooperate with the industry on this direction. And the second, more focused on science. We found that we're still not sure. Many people are ask this question. We still don't know the answer, but it's new. It's a phenomenon. So for example, if the fiber battery with a diameter of 1 millimeter, it's just one fiber. And then we make a 100 micron small fiber, twist them together to form the big fiber also with the same diameter of 1 millimeter. We found that for the later case, the flexibility is much better than the first case. And I'm not the expert at the mechanical part. Maybe Professor Zheng can feedback about this, some solution, some answers. But it's highly repeatable. And I don't know, maybe for flexibility, not only the materials and also the microstructures also play a key role for this part. So very interesting phenomenon. And here's the flex. And then I will discuss the last part about because we mainly weave this fiber batteries into the clothes. So we found that based on the interwoven structure of textiles, and this kind of structure also can make this fiber batteries, although maybe the fiber batteries is how to say that, is flexible, and after with the clothes, sometimes the flexibility can be decreased or just touch not good, and looks not very good. So I think the weaving technology is also important for the fiber battery. But I also not this kind of expert. I think need more research to understand, to find what kind of methods are very effective for this fiber battery. Okay, so I just briefly discussed the report. Yeah, and probably come back to Professor Yang. Or Professor Zheng can comment on or give some explanation about why for my second point. It's very interesting.
I can give you maybe some quick feedback according to my experience about why at the same. I think what you mentioned is that at the same diameter, or at the same volume, if you make a thick fiber versus a multiple smaller filaments and then twist them together, the pliability is better. Or we go back to the way that it's probably less stiff, right, from a mechanical point of view. So I think that's quite common in textiles, where you see the yarns that we make. I'm not from textile, but my department is the textile department, right, for many years. So from a textile point of view, if you make smaller filaments or smaller fibers and then twist them together, that's how we make yarns for weaving clothes, etc. And the advantage of having this multi-dimensional or hierarchical structure from a small to a big is that in several ways that you can increase the mechanical durability, and because the fibers have some space, very tiny space among the fibers, and they can somehow slide a little bit, very little, and that structure is very effective to release all the stress that's been applied. So that means that I think in Yuan's talk also mentioned the radius of or material, that the bending, the strength of material when it's bent is proportional to the thickness of the material. And so basically you are doing a bit thick material, and then you convert this thick material into a multiple layer of very thin material. So you bend, and when the material are not adhered, not adhere to each other firmly, that means there it can be some sliding, very little bit. So you can consider this multi-layer as very thin layers of each. And therefore, when you probably, my feeling is that probably when you bend them, you can individually consider each fiber as one substrate, and therefore, because you effectively decrease the substrate, and then so-called your flexibility will be increased, even though the materials are identical, right? From a structural point of view, that will be a very effective to create this kind of sliding or not firmly attached structure to resolve the problem. That's what I think.
Okay, that's very helpful. Yes.
Right.
Thank
so
you.
Maybe Yuan can supplement, and also Yuan's structure is very different, right? Because you are trying to solve the problem from a more conventional point of view. And I see that your performance of the battery is outstanding. And Yuan, maybe you can talk about how do you, from this aspect, how do you address trade-off?
Yeah, the flexible batteries trade-off is a major challenge inside. I agree with Professor Peng that at first I think there be more fundamental understanding. So, for example, I think more mechanical simulations are actually needed for the field to really understand. So, what happens during the trade-off? During the binding process. For example, we actually found that sometimes in some configurations, so the materials, the active materials, the foil actually not the limiting factor, but the packaging is actually the limiting factor. So it actually, if for conventional pouch cell, the lumen pouch actually break first. So then how to engineer the pouch actually may have more to make batteries more flexible. And for pouch, the challenge is that it needs to be air and moisture resistant. And this actually, the requirement is much higher than solar cells. And then the food packaging is actually very high, so that the conventional packaging materials are often considered actually not suitable for batteries. So this is a challenging part. So because in my project I focus more, first the energy density needs to be high, and then how to make it more and more flexible. So then I think I believe there will be some very exciting new ideas that can actually achieve goals together. So for example, the fiber battery, so Professor Peng showed is 110 watt-hour kilogram. I think that's already really high and really open doors to many possible applications. Then in the more, say, the thin film like cells, then I think some better binders. Okay, because we find that finally during the binding, the one big problem is the delamination. I'll say that just the sliding between different layers. If you have a good binder, for example, alginate, so it's a good, I mean, it has a better adhesion, but it has its own problem. And also, for example, the carbonyl tubes sometimes can form a network in the electrodes, so that all help to enhance the adhesion or say the binding of different materials, and that's actually help a lot on enhancing the flexibility of batteries, especially in this configuration similar to the conventional batteries.
Right. I think that's the key. I think follow up with this. So maybe another more specific questions to Yuan, and I think this probably is not really seen in Professor Peng's work, because in Yuan, I think in your cell, when you demonstrate it, it looks like the cell has been structured into internal segments, right? And then when you bend the cell, it looks like you are bending the cell at the thinner part.
Yeah.
Which is more flexible, I believe, and then the more like a thicker part, which should be like electrode areas. So when you actually bend the cell, is there any specific issue in that thinner part, and does it like fatigue very quickly as you go?
That's a good point. So the thinner part, you actually need to pay attention. For example, in some of our publications, we show that if you actually have a tape to support the metal foil in the thin part, so that actually will reduce the strain inside a lot and make it less, more resistant to fatigue. Okay, that actually will enhance the flexibility a lot. For example, something, I don't remember the exact number, but for example, enhancing the bending time from maybe 5,000 to 20,000. So just put a piece of tape, put a piece of tape at the interconnection. So we run some simulations basically due to the flexibility of the tape. So the strain in the metallic interconnection field actually can also be reduced. Yeah. So it looks like an engineering solution, but there's actually science behind. Yeah.
Right, I believe so. We also been doing this study for quite some time. So let's continue with the second. I think the second question, and both of you have actually mentioned, when you want to integrate the batteries, we need very good encapsulation, and the encapsulation, one is to make sure the battery work. On the other hand, encapsulation is also facing some issue for wearables in terms of this safety issue, right? Because unlike a conventional battery, you can encapsulate in a stainless steel box. For wearable, it's impossible, right? So I would like to maybe also about your feeling. How do we further develop this maybe new type, or how do we engineer the existing ones? Because as Yuan said, seems like there's no replaceable material so far in a larger scale to replace this aluminum punch. And in Professor Peng's work, I know that in your fiber-shaped batteries, it looks like you use some kind of polymer composites to wrap it around, right? How the stability of this new encapsulation material is to your battery, we are also very interested in. So maybe either of you can start.
Okay, so I think this is a very good question. And also, I think for this discussion, if some experts from the industry will be very helpful. In fact, for us, and the main difficulties are like that. how the people, people want to use the fiber batteries, what do they want? And most time I ask them and they don't know, because this is the total new technologies. So then there will be many problems. You mentioned safety. Maybe safety is okay for us because we have made a lot of safety measurements, include no explosion, no firing, and also even in water, no problem, high temperature, no temperature, they're all okay. But okay just based on the lab, not in the new products. And also you made a flexibility, how flexible they want. Maybe it's okay now, no problem. So for the cooperators, and there are many also scientists or just engineers, not the salesmen, not the people that want to really use this technology. So based on this information, I want to summarize several parts. So the first about you mentioned the stability and the proper part. And I discussed with a lot of people, they think for the energy density of 100, it's good enough for many applications, no problem. And then the more care about the cost, how expensive it can be, can we provide. And it also depends on different applications. So then this technology is more related to the market. So I think this is the proper part, and I think flexibility, safety, and for safety, we also measure when you wear under clothes, there will be it will affect the health of our body, and we also started this part, and it's also okay, but it's also just we think it's okay. So because no similar technology, no similar products we can know or can understand this problem. So I think for the property part, and it's not only related to the scientist and the part mainly to the engineer and the people to use them, and also for the second part, and it's very easy, very difficult for us to produce these fiber batteries at a larger scale. We cannot find the facility at the market, for the production at a very large scale. So we have to design many parts by ourselves. We can to build up the production line by ourselves, but we are not experts at the mechanical engineer. So it's very difficult for us to how to, although we have it very high performance at the lab, how to make sure it can be continued at the larger scale. It's facilities, and also not only facility, and there are a lot of many production parameters, how to control them, and how to make sure every step to be efficiently connected with each other. So I think this is also very important. And for the third part, and also very difficult, is that it's possibly easy for Professor Yuan, because there are a lot of standards for the film batteries. But for the fiber batteries, no standards. How we judge these fiber batteries are good, how good it is, how useful it is, and no standards. So I think it's also very important to build up standards so different batteries from different labels can be easily compared with each other. And it's also a challenge. And even for, I just come back for the flexibility, for example. How you bend it, right? Very slowly, very quickly, and it will be different. How about the bending angle, how thin it is? And especially for our fiber batteries, it's very difficult. And so I think, in other words, there are a lot of things designed to do. I think I also discussed with Zhe is editor-in-chief for this EcoMat, and I also discussed with the other editors from top journals, from the other top journals, nature sister journals, And the editors are also very interesting because they think this technology are very close to the market and very useful for many applications, but they're still not available at the market. They think it may be possible in 5 to 10 years, so they want to push this direction forward. And they also ask me what we can do to speed up the process. So I think I provide many difficulties, and also there are new directions. And I think for this direction, we need a different backgrounds of people to cooperate together. So I think maybe by this way, we can nearly push this direction very quickly, go ahead. And if everything good, we tried for us. It should be okay for us to have these products in several years. I mean, at a larger scale. For small scale, no problem. Many people are trying to use them, but not larger scale. They're just very interested in the technology. Oh, it's a new stuff. Well, let me try. Just like that. Not nearly very big market to use them. Not yet. Okay, so yeah, may I talk too much? Okay.
No. I think that's really important, and we actually also have a spin-off working on flexible battery, and we probably face similar problems as you have.
Yes.
Between the interface of academic transfer and then the market. We do have some discussion about the one you talk about. How do you actually compare data, not as a standard, but we suggest a figure of merit for flexible battery. I think we published in Jewel in 2020 or 2021 about a very short article about how do we consider the energy density versus flexibility of a real cell, not just an electrode, and how do you judge a thick electrode, not very flexible, a thin electrode, very flexible. How do you actually consider that? Because at the end of the day, I think as Yuan talked about, one piece of paper is a paper. Looks very flexible. A book doesn't seem very flexible, but at the end of the day, they're identical, right? They are just making up of the same material, but different thickness. And so I think we discussed that issue about energy density versus flexibility in that articles. Right, Yuan, I think I'll go back to you about this encapsulation layer, and you specifically mentioned that that's a big problem, a big challenge. How do you feel about that?
Well, I feel it's a challenge. That means I don't have much solution to that. Yeah. So okay, some thoughts I have. I mean.
You probably not solution. If you raise questions or challenges, and other people probably will think about that, and then they will echo that with papers, right?
Yeah. So for packaging, first, if you think about the banding of a film-like battery, so the packaging is R-side, the most R-side layer. So that means it actually suffer most string. So the string inside is the largest, and the pouch is actually not that. That means not that flexible. And the pouch is made of aluminum polymer layers. So the delamination is actually the problem. So one thing is whether we can make the lamination between the plastic and the aluminum higher. And I have thought about maybe some strategy like having a buffer layer somewhere, so that may help. But it needs to be looked at. Much in details. And basically the trade-off here is you want the package to be flexible, and you also want to be resistant to air and moisture. So for common polymers, for example, I see some past publications using PDMS as encapsulation. So it's very flexible and even stretchable, but basically the air can go inside very quickly. So basically, this is the trade-off, and maybe adding, for example, ceramic, maybe graphene or boron nitride sheets inside will help to enhance things to suppress the penetration of the moisture inside. But I think this is a very interesting topic. So people seldom think about that or didn't focus on that too much. But I think this is actually very important for practical applications.
Right, thank you, Yang Yuan. I think that's important, extremely important. There are not many papers, right, publications or even patents about encapsulation layer, but to me it seems to be probably even like a problem number one if you would like to put things into real product or market, right? Unless others can be improved by materials and structures, but then the encapsulation is something you must have, and then you must be very good with. Right, I think the time is up. We have been spending fantastically an hour and 40 minutes on the talks and the discussion, and due to time limit, I have to wrap up this symposium. And again, let me thank Professor Peng, Professor Yang for two excellent talks, and then the follow-up discussion. I think there's a huge challenge of flexible batteries. Of course, it's something that will happen in the future. We're gonna need them. We're going to use them. There are gonna be many products requiring this very flexible, pliable batteries. The question or challenge probably will be a balance of energy density to some applications, flexibility, of course, safety in terms of stability, and then the safety when you use it, when we bend it, and then the lifetime, right? We need them to have lifetime. And probably at the end of the day, when for different applications, you look for scenarios such as washability, abrasion, or all that, or even temperature, high temperature, low temperature, that environmental issue, that can also be very challenging. And as Professor Peng said, it requires many people from mechanical point of view, from chemical engineering point of view, from processing point of view, and even industry for input, and not only just the material scientist, right? So I hope that this discussion will make some sparks on this field and will push it forward. And again, I would like to thank everybody, the speakers, the organizers, and the audience for taking part in this event. EcoMat will have another monthly seminar in March in another topic. I think the forecasting is that we'll have a fuel cell topic in March. So we'll have follow-up advertisement and other stuff. And so thank you very much and have a nice day.
Thank you, Mr.
Okay, thank you. Okay.
Thank you very much. Bye.
Thank you.
Thank you. Bye-bye.